Hello, my name is Leora, and I'm here with Phoebe, Caroline, Joe, and Andrew to talk with you about Aqualus, a semi-automatic research aid for collecting and filtering microplastics in estuaries and rivers. It is widely known that our world is facing a plastic pollution problem. It's estimated that around 269 billion tons of plastic are currently floating at or near the surface of the world's oceans. What many people don't know is that while left in the environment, these plastics break down into smaller particles over time, leading to the creation of microplastics. Microplastics are formally defined as plastic particles that are smaller than 5 millimeters in size. Microplastic pollution poses a threat that is potentially far worse than general plastic pollution. Because these particles are so small, they fall within the optimal prey range of many microorganisms. In addition to getting eaten and bioaccumulating up the food chain, varying sizes and densities make them easily distributed across the globe. They have been found everywhere from inside icebergs in Antarctica to on the beaches of remote islands. And because of this small size and vast distribution, they are extremely hard to gather data around. Research organizations have classified microplastics as contaminants of emerging concern. However, due to the difficulties surrounding data collection in this field, the preliminary research is limited and incomparable across laboratories. This means that the world is not yet in a place to quantify the effects of microplastic distribution on a larger scale. Without this data-driven understanding, there are no grounds to drive policy change and cleanup efforts. While the interest in quantifying microplastic contamination is relatively new, interest from research agencies across the world means that it will be widely talked about soon. Thus, Aqualus is on the forefront of this novel topic, positioning ourselves to tackle the first steps in this process. Team Aqualus went out and talked to experts about their current sampling techniques in order to understand what is currently lacking in data collection and what needs to change to gather data on a larger scale. We learned that overall, this data is limited in quantity, low in accuracy, and unrepeatable across labs. And this is due to the tools that they are using to gather samples. Of these tools, there are three main collection methods currently being used. The first is using bottles, a simple collection technique where the researcher dips bottles into the water to collect a sample. However, researchers are only able to collect small volumes of the water because it has to be stored on board and transported back to the lab to be filtered. Another technique is attaching a net to a pole and dragging it through the water. But with this system, the depth and volume of collection can only be estimated. Finally, a pump-based system allows researchers to pump water from deeper depths with more accuracy, but since there currently is no existing integration of pumping and filtering, only a small amount of water can be collected. After reviewing the deficiencies in existing tools and discussing needs from stakeholders, we have determined crucial system characteristics. The system must process 500 liters of water to collect a meaningful sample based on existing data of the minimum concentration of plastic in estuaries and must do this in under 25 minutes due to the number of samples a researcher collects in a trip. For autonomy and user relief, the system must require no more than 2 minutes of hands-on attention per sample in order to reduce the strain on the researcher. To provide value, a system must sample at any depth up to 15 meters, a maximum depth of most rivers and estuaries in this region, and do this within an error of plus or minus 0.15 meters in order to acquire distinguishable data. To get usable data on concentration, a volume accuracy of plus or minus 2% of the total sample volume is necessary. And to provide a sufficient quantity of samples, researchers should be able to take at least 12 samples per 6-hour sampling trip. Finally, it is crucial to the researchers that microplastics are filtered from the water in the field, and plastics of up to at least 50 microns with a reach goal of 10 microns must be collected. To give you an idea of what value these characteristics bring to this research, we are showing you an example of what collected data looks like with the current tools. This graph, representing data from recent literature that use net-based collection, shows the concentration profile along the water column of samples taken from a river. Due to the varying sizes and densities of microplastics, it is helpful to split the data into two categories: particles denser than water and particles less dense than water, to better show the relationship between concentration and depth. However, since these samples are taken far apart and have low accuracy on both depth and concentration, you can only see a general trend and not much more. Here, we show the quantity and accuracy of data that our system should provide researchers. The relationship between concentration and depth is much more detailed and meaningful due to a larger number of data points, as well as much higher accuracies, a crucial feature in actually understanding the distribution of these plastics. This high volume of accurate data will allow for future cleanup efforts and policy change that are not currently achievable. So we've designed Aqualus to achieve these crucial characteristics. Aqualus can be arranged in various configurations, designed to be operable on nearly any standard research vessel. It contains both autonomous and manual systems to reduce strain on the researcher, but still allow for interference and control by the expert. Overall, Aqualus collects samples at varying depths and delivers filtered microplastics for later post-processing in the lab.
Aqualus contains 5 main subsystems.
These include submersible sensors and a pump that collect sample depth and volume data from the water source, and a depth control system consisting of a motorized hose reel that moves the hose to the desired sampling depth. The water flows through the hose to the fluid direction system that directs the water into the appropriate sampling stack. Each of these stacks houses filters which filter the plastics between 5 sizes as the water sample flows through them. The water is then discarded back to the water source, capturing only the microplastics to be delivered to the researcher. The user interacts wirelessly with the system through an Android app. Behind this mechanical system lies a communication architecture in which the sensors, pumps, and electronic components interact through a core Arduino processor. This means we take the raw data from the depth and flow rate sensor and use it to inform the commands to the pumps, motors, and valves. This Arduino also wirelessly communicates with the user interface, taking intended sampling parameters from the researcher and communicating back actual collected data. Subsystem 1 houses submersible pumps that bring water on board through a hose, and an above-water flow rate sensor that is used to control the flow rate of the sampled water. By using a pump, we can rapidly collect a large sample of water from a wide range of depths and easily control and measure the flow of water with a flow rate sensor and control feedback. The diameter of the hose and all other coupling components is calculated based off of Poiseuille's law that dictates the movement of an incompressible fluid in laminar flow through a pipe of constant diameter, conditions that describe our system well and result in a diameter of 0.5 inches. In order to control this feedback and hold a steady flow rate, something that is necessary for repeatable samples, we designed and tuned a PID controller for the pumps. This graph shows the reaction of the flow rate in blue, and you can see that after about 30 seconds, which occurs in the cleaning process when exact flow rate is not necessary, the flow rate settles to the desired rate shown by the gray line. This means that we can reliably hit the same flow rate so the same sampling conditions can be replicated for comparison.
Subsystem 2 autonomously controls the depth of the pumps while sampling, a crucial system to take a difficult task away from the researcher and provide a high level of accuracy that is not currently achievable through existing sampling techniques.
This compact and reliable hose reel system with mechanical and electronic slip rings extends our hose end wiring up to 15 meters. This consists of a submersible depth sensor that informs a motorized hose reel with depth readings and actuates when the hose is not at the intended depth. The high accuracy sensor eliminates manual error and allows us to automate as much of the system as possible. This controller is active throughout sampling so that it can hold the collection system within the necessary depth range, even in moving water. The water pumped from the depth system and through the hose reel is then sent to our fluid direction system. We've chosen electronic solenoid valves to direct the water either through the filter stacks or directly off-board to clean the system between samples, a necessary step to avoid cross-contamination. A manually rotating faucet head rotates between 3 fixed positions to distribute the water into our filtration stacks. We designed this manual rotation mechanism to be easy to use, incorporating spring-loaded ball plungers that compress with sufficient force. These allowed us to manufacture a rotating head that moves with the force of a hand but snaps into the 3 predefined locations centered over the filters. Finally, the water enters into our 4th subsystem, which houses our actual deliverable to the researcher, a filter stack composed of color-coded filters that reduce in mesh size from 10 to 500 microns, filtering plastics between 5 sizes that can be taken directly back to the lab for post-processing. The filtering system is one of the most novel components of Aqualus and allows us to capture microplastics of even the smallest sizes, a quality that other collection techniques cannot achieve. Filtering large volumes of water through fine meshes is challenging due to the pressure required to break the surface tension. This is a reason that researchers are not currently able to work with small mesh sizes and proved a significant factor in our design choices. We developed an experimentally based model to ensure the functionality of this crucial feature. As pressure is a limiting factor, we set up an experiment with justification from existing studies to relate pressure and flow rate through the filters Aqualus actually uses. The raw data from this experiment can be seen here. Our experiment gave us critical insight into the function of these filters. Although the water could not flow at the necessary 20 liter per minute flow rate through a 10 micron mesh without back pressure, a 50 micron mesh could sustain this high flow rate, and Aqualus still accomplished its baseline goal. Apart from the physical system, we created the user interface to give the researchers an easy way to communicate with Aqualus. The user simply has to select the depth to sample, the desired flow rate, and the volume, and the app then sends the parameters to Aqualus and commands the sample to start, sending back real-time information to the screen.
Now, let's take you all on a sampling trip. The process begins with the researcher attaching the hose reel and system to the boat. The researcher then inputs the information into the Aqualus app. Then, the researcher puts the filters with desired mesh sizes into the appropriate stacks. Once that is done, the researcher clicks Start in the user interface. Allowing for the researcher to do other work, Aqualus automatically pumps water through the pipes for cleaning. After the cleaning is finished, Aqualus pumps water at the desired depth into the filter stacks. Once one stack is completed, the user rotates the faucet head to the next step for collection at each depth. The researcher removes the filtration stacks containing the plastics and takes those stacks to the lab for post-processing analysis. So far, every individual component of Aqualus has been manufactured and testing for functionality. All sensing, computing, and electronic components have been combined with their direct counterparts. Each subsystem has been manufactured and validated and are ready for final integration and full system tests in the future. Our largest scale tests were performed in the Pottruck pool. The purpose was to validate the motorized components and depth control, as well as pumping water from deep depths at a controlled flow rate. It proved extremely successful and showed that Aqualus could function as designed in a controlled environment. Additional validation procedures with individual subsystems predicted how Aqualus will perform in its final form. To ensure that Aqualus can actually collect samples, we performed a yield test through our filtration system by running a known quantity of microplastics with known size through the filters and measuring what was collected. This resulted in average yields of 98% with a confidence interval of plus or minus 0.02%. Flow rate tests through our completed filters also resulted in exceeding our maximum rate of 20 liters per minute through any mesh size above 50 microns. We calibrated the flow rate sensor to validate the accuracy and volume measurements, a key system characteristic. This sensor emits a series of pulses to transmit data, but by default only reports values every second. To achieve the required less than 2% error, we needed to relate these pulses to known flow rates every millisecond. Therefore, we developed an experimentally based model shown in this graph to fit a flow rate curve to pulses in real time to accurately know the flow rate at any moment. This was later validated to ensure Aqualus precisely knows the volume of water sampled every millisecond. The next steps in validation would have been to test Aqualus in real water sources. A Schuylkill River test would have informed us of Aqualus's functionality in external conditions, and a full system test on a boat with active researchers would have helped inform us of quality and user interaction. Both the samples would have been sent to the Philadelphia Water Department to be processed by researchers in the lab and provide us with fully analyzed samples. So, up to this point, we are confident that Aqualus can individually hit every one of our crucial system characteristics and deliver meaningful data to researchers. Now, with an understanding of Aqualus and the characteristics we have been able to achieve over the year, we can show a quantitative comparison of how our system performs compared to existing solutions. Here, you can see bottles, a sampling technique that, while having high volume accuracy, lack in every other characteristic. Nets can collect a greater quantity with higher speed and better post-processing, however lack in autonomy and accuracy. Pumps alone have good volume accuracy and sample quantity, but no level of post-processing or autonomy. And finally, you can see Aqualus, which can simultaneously perform well over all characteristics and deliver unparalleled autonomy, taking away the tedious and time-consuming tasks from the researcher. With Aqualus successfully meeting our system criteria defined by stakeholder needs, we went back to the same researcher to discuss our solution. Our stakeholders overwhelmingly approved our design choices and were extremely pleased with our work. Team Aqualus looks forward to donating our system to researchers to continue to improve into the future. Microplastics are a huge problem, but we do not know the full effects they are causing to humans and the environment. Aqualus is on the forefront of this under-researched field, providing a way for researchers to accurately and repeatedly gather data, and giving scientists a new understanding the lasting effects microplastics will have on the Earth. The environment is the pressing issue of our generation, and Aqualus is a solution taking steps towards controlling and regulating plastic pollution. Team Aqualus is composed of Phoebe, Joe, Leora, Andrew, and Caroline. We want to give a huge thank you to all our mentors that have guided us through the year. Thank you to the Penn Water Center for your continued support and grant money. Thank you to our primary faculty advisor, Dr. Drelmack, Graham, and to the many other technical advisors who gave us guidance this year. Finally, thank you to our 3 amazing teaching assistants for their continued support.